Today we're talking about a few examples using the fundamental effects to kind of study different scenarios from the points of views of different observers. And we'll also talk about a kind of a version of the twin paradox where we don't really need to rely on acceleration, where we have three observers or three spaceships. So it's a different scenario that can be analyzed more directly just using the fundamental effects of special relativity. And I will also give an elementary derivation of the velocity addition formula using these fundamental effects. So let's start with some examples. Examples on fundamental effects. And I'm essentially following Maureen's chapter 1. So the first example is about time dilation. So consider this scenario. So we have a frame S where you have two planets in that frame. So they're sitting at rest in this frame. And they're a distance L apart, planet A and planet B. And they have synchronized clocks, so they're in the same reference frame. So let's say the clocks read 0 at some point. And imagine a rocket or a spaceship that's at this time in the same position as planet A, so something like this. It's moving with velocity v in this frame. And at this time, it's synchronized to read 0. So the clock on board this spaceship reads 0. Okay. So in the frame where the planets are stationary, how long does it take for the rocket to reach from A to B? Well, it travels a distance L with velocity v, so it should take L over v. So when the rocket reaches planet B, so again, this is A, this is B, this is L, we're still working in the frame of the planets. So now the rocket is here, still moving with velocity v in that frame. So at that point, these clocks have advanced by L over V, right? They're synchronized, they're in the same frame. So now the question is, what does the clock on board the spaceship read? And we know the answer. So in this frame, if there's a proper time tau corresponding to the frame attached to the spaceship, we have time dilation. So more time has passed, right, in the frame of the planet. So this should read that L over V over gamma. Okay. But that's all reasonable. So this is a simple scenario. So now here's kind of the apparent contradiction. So you may ask, well, from the point of view of the rocket, then the rocket is stationary. And what happens is, well, we have A and B. They move this way with velocity v. So that's sort of this beginning scenario. And then the end scenario is, again, the rocket is in the same place. Spaceship is in the same place now. A has moved over here, still moving in that frame. and now B has reached the spaceship. Okay, so from the point of view of the spaceship, those A and B are moving. So time dilation kind of works in the opposite direction, right? So the clocks on A and B are ticking more slowly from the point of view of someone on that spaceship. But then the times on the clocks, I mean, they should not differ. These two are at the same point in space, and they can compare notes. So if this is reading L over V over gamma, this is reading L over V, which is a longer time, even though its clock has been ticking more slowly from the point of view of the person on the rocket. So what's up with that? How can we make sense of this? Well, the resolution comes from thinking carefully about the clocks and the rear clock ahead effect. So essentially, let's say again, when these two are meeting, when the spaceship and planet A are meeting, so they read 0. But now, from the point of view of someone on board the spaceship, A and B are in a moving frame. They are separated by some distance L. So that's the proper length in the frame that's moving with the planets. And then the rear clock, which is the clock on planet B, at that point should be ahead. So this is not going to be 0. It's L V over C squared. Okay. So now, what's happening from here to here? So now we know this clock reads L over V over gamma. So what can we say about what the clock on planet B reads? Well, if clock on the spaceship reads L over V over gamma, during that process, the clock on planet B has been ticking more slowly by another factor of gamma. So it should have advanced by L over V over gamma squared. But it had a head start here. So LV over C squared. So this clock over here, so I wish I could squeeze it in. Let me see. I think I probably can. So this clock over here should be reading LV over C squared. The reading at this event plus LV gamma squared. This much time has passed on board the spaceship. The planet is moving relative to the spaceship, so it's ticking more slowly by another factor of gamma. So that should be the reading. So is that the same as L over V that we concluded from analyzing the situation in the frame attached to planet B and A? So let's see. Let's work that out. So what we have here is LV over C squared plus L, was it over V gamma squared? Yeah, L over v gamma squared. So we know gamma is 1 over square root of 1 minus v squared over c squared. So 1 over gamma squared just becomes, we square it and then invert it, so it becomes 1 minus v squared over c squared. So then this time becomes LV over c squared plus L over v 1 minus v squared over c squared, which is LV over c squared plus L over v minus 1v cancels out, so LV over c squared, they cancel out. So that is indeed equal to L over v. So there's no contradiction between what the clock reads if we sort of switch frames and analyze the situation from different frames. We have to be careful with this loss of simultaneity, this rear clock ahead effect. All right, so let's now work out another example. So this is the scenario. So we have a platform, and there are 2 paint bombs on this platform. And at the same time, in the frame of the platform that we call t equals 0, let's say, these 2 paintballs explode. And they mark both the platform, of course. So let's say that proper length in the frame of the platform is L. They mark the platform. They also mark a train that's moving with velocity v, relative to this platform. All right. So the question is, according to someone on the train, what is the distance between these 2 marks on the train? Well, so essentially, like that, those 2 paint bombs are simultaneous in the platform frame, right? So they essentially measure the length of that interval between 2 marks in the platform frame. So we find that to be L, but then we know there's length contraction. So the proper length in the train frame must be larger by a factor of gamma. So in train frame, the distance between marks must be gamma L. So it's measured as L in platforms frame because of length contraction. Now, let's think about this story from the point of view of someone on the train. So we're saying that the distance between the marks is gamma L, it's larger than L in the frame attached to the train, but you know the proper length between the paintballs is L, right? And the platform is moving with velocity v in the opposite direction relative to that frame. So that length is length contracted. So it appears that the paint bombs are even at a shorter distance, like L over gamma in that frame. So how come, what's happening that we end up with a distance of L times gamma in the trains frame in this scenario? Okay, so let's analyze this. So trains frame. So in the trains frame, well, we see the platform that has a contracted length L over gamma moving this way. And there are paintballs at the two ends. But again, we have to be careful that these explosions that were synchronized in the platforms frame are not synchronized in the trains frame. So this is the train that's now stationary. So if we have the rear ahead effect, let's say this reads 0, and that's the time of an explosion. So an explosion happens here. This paint bomb doesn't read 0, according to the observer. On the train, it reads minus, right? It's in the front. We're moving this way. LV over C squared. So then when it explodes, of course, it has to reach 0, right? We know explosions correspond to a clock reading of 0 on the platform. So then, and this is a train, the platform will be somewhere over here. And this mark is already left there from the first explosion. So let's put that there. And now another explosion happens over here and leaves the mark here. Okay. So now this clock is reading 0. Okay. So this length from here to here is L over gamma, according to someone on the train. The proper length of the distance between the two paint bombs on the platform is L. It gets contracted to L over gamma. Now we have to see what this distance is from here to here, right? The back of the velocity v, the back of the train has now moved by some distance and is separated from the mark on the train. So let's see how we can figure that out. So we're saying this clock over here, that's at this point is reading minus LV over C squared. And at this point, it's reading 0. So this one that reads 0 at this point should be reading plus LV over C squared. Okay. So that, we're comparing same clocks, right? The clock here at this endpoint. So that's the time that has passed on the platform. There's a difference in between the readings of the clocks on the platform. So the time that has passed in the frame of the train must be longer, right? That's the proper time for this clock over here. But then the time that has passed in train's frame must be larger by a factor of gamma because of time dilation. So time passed in train's frame that we're working in is equal to gamma LV over C squared. over this time, the platform is moving with velocity v, so this distance should be that time times the velocity v. So it should be gamma L v squared over c squared. All right, so now let's see if we can figure out the distance between the mark on the train from these two. Well, that distance on train measured in train frame, that's what we're doing, right? Measured in trains frame. That's L over gamma plus gamma LV squared over C squared. So, so I can factor out a gamma L. Then I get 1 over gamma squared plus V squared over C squared. 1 over gamma squared is 1 minus V squared C squared over C squared plus V squared over C squared. That's gamma L. So that's consistent with what we found when analyzing the problem in the other frame, in the frame attached to the platform, right? That was a simpler argument we found just from length contraction, that the distance between those marks must be gamma L in the trains frame. Now, looking at the same story in the trains frame, we recover the same result, even though the length of the platform, or the distance between the two paste bombs on the platform, is shorter again because of length contraction, according to this person that's riding on the train. Okay, so now let's switch gears a little bit and talk about velocity addition. So the situation we're considering is we have a frame S prime that's moving with velocity v relative to some observer. And then there's an object that's moving with velocity u relative to S prime. And we want to see what is the velocity of that object from the point of view of this observer that's standing still outside. So let's consider the scenario where this object moves from this end to the other end. Let's imagine we have like a box there or a train or something, and it moves a distance. So let's call that proper length L. Right, it moves from this end to the other end, which in S prime corresponds to moving moving by a time like L over U. Okay, so from the point of view of this observer, we have, let's say, this train here, it's moving with velocity v, and then this object is here, it has that relative velocity u, so let's not write that because that's with respect to this train, and then when it reaches the end, again, it's here. Train is still moving with velocity v. So that whole process, this moving from here to there, has happened with some velocity w. According to this observer that's, again, standing outside and not moving. All right, so what can we say about these? So the length, if that has a proper length L, according to this observer, we see or she sees a contracted length L over gamma. So the process is, this object is at the beginning here, and then it's moving with velocity, let's say W. The front end of the train is moving with velocity V. Initially, it's the distance L over gamma ahead. So again, if we consider some sort of a diagram here, you see this is at L over gamma. That's the front of the train. That's ahead, but it's moving faster with some velocity sorry, it's ahead, but it's moving more slowly with some velocity v, and then this ball that's thrown, or that object that's moving inside the train, is moving faster, but starts at the origin. So again, we can write like W t is going to be L over gamma plus Vt. So that t, let's call it Tg, the time that has passed on the ground, according to this person standing on the ground. So then we find L over gamma is W minus V times Tg, and Tg is L over gamma over W minus V. So that's one way of calculating the time it takes for this object to move from one end of this train to the other end, assuming that the proper length of the train is L. And of course, I should say that gamma is, of course, with respect to V, right? The relative velocity of the frame. It's 1 over square root of 1 minus V squared over C squared. All right. So now let's look at the same story, but kind of from a different perspective. So let's think about the times on the clocks that are on this train, okay? So again, it's the same situation. So we see, again, there is this person standing on the ground. There's going to be this velocity W that this person would observe for the motion of that object that's thrown inside the train. There is this train that's moving with velocity V. The train has a length L over gamma according to this observer on the ground. So let's say the time that this object leaves the back wall is 0, like on the train. So the clock inside the train reads 0 at that point. So according, again, to this person standing up on the ground, the clock on the front should read, so we know that the rear clock is ahead, so this should read minus LV over C squared. It should be behind. The one in the front must be behind. Now, when that object hits the front wall, well, we know how much time has passed in the frame attached to the train. So proper length L, velocity U with respect to the train. So that should be reading L over U. L over U. So, which means that the time that has passed on the train is L over U plus LV over C squared. It went from minus LV over C squared to plus LU. So at this event, the ball hit in the front wall. This clock over here should read L over U plus, right? Started from 0. L over U plus LV over C squared. So that's the reading on this clock, and essentially the time that has elapsed in this moving frame is going to be that, because it went from 0 to this. Okay. So now, what can we say about the time that has passed on the ground? Again, we know we have time dilation, right? So the moving clock is ticking more slowly, so more time has passed on the ground. So TG is going to be gamma times all of that. Okay, so we found two expressions for this TG, the time between these two events, the object leaving the rear wall and hitting the front wall. So one expression just involves like V and U, and the other expression involves this W, and of course also involves V. So they must be equal to each other. So that's also equal to L over gamma W minus V. All right, so from here, we want to find that W, the velocity, to the observer on the ground, to the outside observer. In the Galilean or Newtonian kind of regime, of course, this W would simply be U plus V, right? So it would be good if the limit for small velocities compared to the speed of light to reduce to U plus V. So let's try to figure that out. It's just some algebra here. So we can write W minus V is L over gamma squared. I divide by gamma divided by that whole thing. So let's say 1 over L over U plus LV over C squared. So the L's cancel out, right, from upstairs and downstairs. 1 over gamma squared was a simple thing, so that was 1 minus V squared over C squared. That's 1 over gamma squared. And then here, what I have is, I have 1 over U plus V over C squared. It looks like it. Yeah, and then, of course, yeah, so that's W minus V. So let's see what W becomes. So W becomes V now. If I take V to the other side, plus all of that. So 1 minus V squared over C squared over 1 over U plus V over C squared. I can find the common denominator. So that becomes, again, I have this 1 over U plus V over C squared. V multiplying that is going to be V over U plus V squared over C squared, like V multiplying this, plus 1 minus V squared over C squared. So those cancel out. That's good. Then I can multiply the numerator and denominator by a U. So I get V plus 1 times U is U. 1 plus V times U over C squared. So that's the famous velocity addition formula. Velocity addition. And it's easy to see if v and u are much smaller than the speed of light, then we can forget about that vu over c squared. That's a tiny number. So it does go to the Galilean limit. All right, let's continue our discussion with an example. So this is based on problem 121 in Maureen's book. So problem 121. And it's called modified twin paradox. It's essentially a version of the twin paradox that does not need acceleration. So instead of using two reference frames, having one twin staying on the Earth, another going somewhere and coming back, imagine we have three observers. So first, at t equals 0, observer A is stationary, so that could be like the twin staying on Earth. Observer B is at the same position, and it's moving to the right with velocity v. And then there's another observer somewhere far away that's moving this way with velocity v. So let's call that observer C. So we have three observers. So what's happening is, well, A is just sitting there, and at some point B and C will be at the same position. So that's a bit later. And when they are, so at this point, these two sync their clocks, so they both, let's say, read 0, A and B. And at this point, B tells his time, the time on his clock to C. So C synchronizes his time to that. So they get synchronized at this point. And then kind of the motion continues until C reaches A. So C throughout, and B is somewhere out there, B. So throughout this motion, all of the observers are in inertial reference frames. Nobody's accelerating. Yet it looks just like the twin paradox, right? So if, you know, the classic twin paradox is B is one of the twins, it moves away somewhere at this meeting point, essentially C continuing but having the same time as B, syncing their clock, is effectively the same as B turning around and coming back. So then the twin paradox entails comparing, let's say, TA and TC at this point. All right, so it's a version that can be analyzed kind of more directly without having to think about acceleration and non-inertial frames. Yet, mathematically, it gives the same result. Okay, so let's first analyze this in frame A, which is kind of the easiest version, or the easiest frame to see what's going on. So those are the pictures for frame A. Let me keep one of them at that handoff position where B essentially tells C where to put her clock. Okay. So if I look at this story in A's frame, So let's say that's position, that's time. A is just sitting there at the origin, right? So that's going to be the rod line of A. So for all times, so these are times and positions measured in A's reference frame. A is just sitting there. B starts at the origin. So at this point, they read 0 on their clocks. Let's say they're at position of 0. And B is moving away from A with constant velocity V. So there's going to be a slope, a line of slope corresponding to V over here. So let's say that's B. C is initially somewhere far away, right? Let's say somewhere over here. And then it moves with velocity minus V. So that's going to be like the reflection of this line, something like that. So this would be line C. Okay. So let's see. So in A string, that's going to be TA, right? That's the time observer A will read on its clock. All right, so how can we calculate these times or make sense of them? Well, let's say at this point where B and C synchronize their clocks, the clock on B reads, so B reads little t sub B, right, at that point. So that means C will also at that point read the same, little t sub B. But this point corresponds to a time here. So let's say that's TA, what A reads. So what should those times be? So in this reference frame, A is sitting there. B has been moving. So there is time dilation. So that TA must be larger than TB. So TB, so TA must be gamma TB, which means TB is TA over gamma. And this is, of course, gamma corresponding to that velocity V. Okay. So then at this time, C now has the same time. And then in A's frame, there's going to be another little TA time that passes. So TA, capital TA is going to be 2 this little TA. But the time that passes on C's clock as she moves from here to here, from the handoff location to meeting A, again is going to be related to TA with the same time dilation factor. So let's say there's going to be another time. So let's say here, C reads TB, that initial thing, plus little tc. But again, these two must be the same. They correspond to the same TA in A's frame, and they have the same absolute value of velocity. So that's just 2 TB. So that's capital TC, the time that C reads there. So TC is going to be just 2 little TB, and that's 2 TA over gamma. So from this, we conclude that TC is TA over gamma. So C is indeed, C reads a shorter time, and it really corresponds to the time the traveling twin would read if the traveling twin turned back at that meeting location between B and C and came back to Earth. So that's like one version. We're essentially doing the same thing as the standard twin paradox. Oops, here I want capital. Yeah, that's correct. As a standard twin paradox, but without resorting to an accelerating frame at the expense of having like a third observer that starts far away, moves toward the Earth, moves toward observer A, and then synchronizes their clock with B's clock when they meet in the middle. Now, so that's kind of the easy frame to analyze this. We can analyze this in other frames. So I think what I'll do the analysis maybe in B's frame. That's possibly the hardest frame to analyze things, because then in B's frame, A and C will be moving at different velocities. And then I'll leave the analysis in C's frame as an exercise. That's actually like a similar difficulty, because then B and A also will be moving with different velocities. But yeah, let's do the analysis in B's frame. So same story. In B's frame. So again, let's draw those pictures. So sort of what we see is now B is sitting here. Remember, B in A frame, B was moving to the right, A was sitting there. So now B is sitting there. She will see A moving to the left with velocity V. Right? So that's what B sees. And then what's happening to C? Well, C is moving, C is somewhere over there, and is moving this way with some velocity. Let's call it U in this way. So how can we figure out what U is? Well, we know in A's frame, C is moving with velocity V. So from the point of view of B, she sees like a frame that's moving with velocity V, and inside this, there's an object C that's moving with velocity V relative to that frame. So the velocity B would measure comes from the addition, the velocity addition formula that we derived. So U is going to be V plus V over 1 plus V times V over C squared. So that's going to be the velocity of C as seen by B. So that's the situation. So let's plot this. So B again now B is sitting at the origin, right, in this frame. A is moving to the left, so A will have a word line like that. So that's going to be A. And then C starts somewhere here and moves faster. I should be careful if light is 45 degrees. This looks awfully close to 45, but yeah, it's not faster than light. It's that velocity there. So let's say this is C over here. This is, just let me change color to make clear what things are. So that's C. And um, and this is A here. A. Okay. So that's going to be the situation in B's frame. So the handoff or the meeting between B and C happens here, and then there's going to be some more time where C now reaches A. All right, so let's see what we can say. So suppose in B's frame, again, this time from here to here, this is, we call that lit T sub B. All right, so that's my time. And let's call from here to here the extra time before the second event, the meeting between A and C. Let's call that, I don't know, tau sub B or something. Well, let's call this T1 sub B, and this is T2 sub B. So again, that's the first one is from the origin to this point over here. The second one is from this point to that point. These are time intervals. So now let's think about what happens. So then the C synchronizes their time with B at that point. So at this point, this TB1 is also the time on C's clock. Now let's see how much time has passed for A. We know A and B were synchronized. So first consider the first leg of the journey before the meeting between B and C. So let's say A kind of at that point reads a certain time. That time that A reads, now from the point of view of B, now A is moving, right? So A's clock must be ticking slower. So when B and C, because they just think, read that TB1, A reads TB1 over gamma, right? So in B's frame, time dilation is happening kind of for A. So A's clock is slowing down. A has taken a shorter time. Okay. So then we have to figure out what happens afterwards. So as there's more progression of time by this TB2, how do clocks on A and C advance? Because ultimately we want to compare the times that A and C read on their own clocks. So then we have to see what's happening here, like what's the condition for A and C to meet. So first, let's see. Yeah, I can draw a bigger picture. So let's just focus on this region. So we have here B and C met. I'm My C is in orange, so C is moving like that way. And my A was in green. So that's my A. That's my C. So this length from here to here, that's the meeting between B and C, right? This is the line of B here. And this time from here to here, we called it T2 in B's frame. All right, so I know that A is moving, right, at velocity V. So let's go down. This was the origin, right? B started over here. And this time, from here to here, we called it TB1. So now we can figure out this length from that. That's how much A has moved over a time TB1 with velocity V. So this length from here to here must be VTB1. So now the situation is, in B's frame, at this point, A and C are separated by that distance. A is moving with velocity V, C is moving with velocity U that we just calculated. So to see when A and C meet, I can write this equation. So I can write the position of C is gonna be like minus UTB2. That's the position of C. That's gonna be minus VTB1, this length. That's the initial position of U at this point, minus VTB2. So TB, so let's bring things to the same side. So V TB1 becomes U minus V. I take this to that side, TB2. Therefore, TB2 will be VTB1 divided by U minus V. All right, so there's going to be a bit of algebra to figure out what that is. Let's do that. So U we said is 2V minus 1 plus V squared over C squared. And then we're subtracting another V from this, and that's multiplying TB1. So TB2 will be, have a V upstairs. I have a 2V minus V minus V cubed over C squared. And then downstairs, I'm getting 1 plus V squared over C squared, which goes up. So what's that? Becomes 2V minus V is V. So that cancels out. So it looks like it's 1 plus V over C squared. 1 minus V over C squared. Okay. So that's going to be this time in B's frame. Now, over that period in B's frame, the clocks for A and C have advanced, but with different gamma factors. So we know how much A has advanced. It's just that time, TB2, divided by gamma corresponding to V. So I can write A's clock, TA. We already figured it has advanced by TB1 over gamma from here to here. And then I have to add a TB2 over gamma. So TB2, we know it in terms of TB1, it's that expression. So it's TB1, 1 over gamma plus 1 plus V over C squared over 1 minus V over C squared, 1 over gamma. I believe that should be the time here. We can further simplify that. So 1 over gamma is square root of 1 minus V over C squared. So let's write that. So this becomes TB1, 1 minus plus this sort of cancels one of these square root factors, right? So I get that in the denominator, and then I have 1 plus V over C squared here. So factoring out that denominator gives me TB1 finally over 1 minus V over C squared. See, there's significantly more work to analyze the same problem in a different frame. So now here I get 1 minus V over C squared plus 1 plus V over C squared. That's 2. Finally, okay, so we relate TA, capital TA, the reading on A's clock at the end of the whole thing when A and C meet to a particular time in B's frame and the velocity. So that becomes 2, this TB1 divided by square root of 1 minus V over C squared. All right. So that's 1/2 of the problem. Now we need to figure out TC, the reading on C's clock, in terms of the same TB1 and velocities and things. So again, we kind of know, we know that C now at this point just reads TB1 because she sync their clock with B. Then from here to here, from the meeting between C and B to the meeting between C and A, we want to figure out how much C's clock has advanced. So that's going to be this TB2 that we related to TB1 divided by the gamma factor corresponding to C's motion. And C's motion is happening with velocity u that we calculated from the velocity addition formula. So let's see. It doesn't even want to select the stuff on the page. Okay. So so let's write TC. So we're saying that's going to be TB1, right? That's the time C met with B and they sync their clocks, plus TB2 over a different gamma. Let's call this gamma C. So what is this gamma c? So it's going to be 1 over square root of 1 minus u over c squared. So that's going to be minus, remember, u was 2v over 1 plus v over c squared, something like that. So this becomes 2v over c, right, when I divide by c, over 1 plus v over c squared, quantity squared. So to take in the common denominator there, let's see what we find. So 1 plus v over c squared. If I expand it, I get 1 plus v over c to the fourth plus 2 v over c squared. And then this is minus 4 v over c squared. Here I have 1 plus v over c squared, quantity squared. So I just expanded this thing. I get 3 terms, and I combine it with this. So that's kind of nice because it gives me 1 minus v over c squared, right? It's going to be 1 plus v over c to the fourth minus 2 v over c squared. So this becomes 1 minus v over c squared, quantity squared, over 1 plus v over c squared, quantity squared. That gets killed off by the square root. So finally, I end up with 1 plus v over c squared over 1 minus v over c squared. So I know that gamma factor. So now we know all the ingredients we want to put everything together. So let's write this TC again. We said it's TB1 plus TB2, but I know what TB2 is in terms of TB1. We calculated that. So that was this expression, 1 plus v over c squared, 1 minus v over c squared. That's my TB2. That needs to be divided by this gamma c. So I get the inverse of that, which conveniently cancels out this factor here. So that's just 2 TB1. So we found TC to be 2 TB1, and TA previously we found to be 2 TB1 times or divided by that. So it's just a factor of gamma, right? So TA we found to be TA um, So let's see, what was that? Sorry, I keep forgetting. So yeah, this was 2t. We just calculated it. TA was um, divided by 1 minus v over c squared. Okay, so that's just 2TB1 gamma, and 2TB1 is TC. So that's TC gamma. So then we find TC again is TA divided by gamma. And it's the same result that we found in A frame. Again, C will have a smaller reading. So the ratio of the times on the clocks of A and C when they meet as seen in a different frame is the same, and it's in agreement with what we found in A frame. So you can play the same game, but now in C frame. We did A frame and B frame. It's a good exercise. I encourage you to work that out. But that kind of takes all the mystery out of the twins paradox, because we can analyze the entire thing without having any acceleration. All right, that's a good place to stop.